Good morning, and thank you all to be here. I'm Rohit Dhamankar, and this is my colleague Rob King. I work for Tipping Point, and I'm a manager for digital vaccine service at Tipping Point, and Rob is a security researcher at Tipping Point. So today, Rob and I are going to talk about how we can do identification and analysis on protocols based on these statistics. So our brief agenda for the day is, first we want to talk to you about why we are exploring this route of trying to identify protocols using their statistical metrics. And one of the examples which we have been extensively studying is Skype, and we will talk about the various coordinates or the various statistical coordinates that we are using for this analysis. And towards the end, we'll also talk about what further work we want to do and the framework which will be available for download from our website. So jumping straight in, the reason for trying to do identification of protocols and trying to look at other ways of doing it is there are at least 3 or 4 problems that are becoming common. So first of all, what we are seeing is a rise in encrypted traffic, and especially the traffic which you would like to ideally block. What we are seeing is malware and botnets have now started using encryption and obfuscation. So it's not an easy job to just look at the packet content and be able to identify the bad part of it and stop these packets. The other thing which we have seen is ports like 443, the SSL 53 DNS, they are open on most enterprises. And what you normally see is these ports are now being also used for covert communications. And in many cases, the traffic which is traversing on these ports really does not look like SSL or DNS traffic. And we want to find a way in which we can identify that bad traffic from good SSL or DNS traffic as an example. And thirdly, we all have used peer-to-peer protocols at some stage, things like BitTorrent for downloading entire Linux distributions, or things like Kazaa, Nutella, LimeWire, BearShare, you name any, there's a big list of them, for downloading music and video files from the internet. And what we are seeing now is even these protocols are changing from first generation to the next generation. The first generation of these protocols did not use any obfuscation or encryption techniques to avoid detection. But now when you see things like Skype, they are purposefully trying to put in obfuscation and encryption so that network-based systems cannot detect these. And that's a problem which we are trying to solve here. So one of the things which is very common with peer-to-peer protocols is they try to hog a lot of your bandwidth. So if you go to a typical university and the dorm environments, almost 60 to 75% traffic could be these peer-to-peer protocols. And as a result, your mission-critical protocols like emails and maybe Oracle databases, your web servers, are not able to use that bandwidth. So with the first generation of these protocols, what has been happening is network-based systems have been able to uniquely fingerprint them, and there are multiple systems which are available out there that can go and rate shape these protocols. And now in their next generation, that is the exact things these protocols are trying to avoid. They don't want to get fingerprinted, and they don't want any kind of system to be able to see them, either block them or rate shape them. So before we dig into more on the statistics, let's look at just a few simple examples of the first generation peer-to-peer protocols. And an example here is the Kazaa traffic. And what you are seeing on the screen is a request which goes from one of the Kazaa peers to another Kazaa peer for downloading a file. And if you look at this request, it looks just like a standard HTTP protocol with the hash of the file being downloaded going in the URL of the protocol. And also if you look at the HTTP headers, it clearly contains the word Kazaa in that. So there are at least two HTTP headers which are containing the word kaza. And so if you want to identify a packet belonging to kaza, it's a simple task because you know the kind of URL the protocol is using, and you also know that the headers contain the word kaza. So in this case, it's an example where the first generation peer-to-peer protocol is just using the standard HTTP protocol, except you notice that the ports are all in high ranges. This is another example of another peer-to-peer application called eDonkey. eDonkey and eMule are very popular peer-to-peer applications in Europe. And in this case, what you see on the screen is a hex dump of the packet. And this is the request packet, which again goes for downloading a file from one eDonkey peer to another. The thing to note here is this protocol is more proprietary. It's not using a common protocol like HTTP or FTP. But if you see a lot of these kind of packets, you can figure out exactly how eDonkey or eMule is working. You will normally notice that the first byte of any request download starts with a byte E3. The next 4 bytes in the packet are actually the length of the data in the remaining part of the packet. And for people who frequently look at hex dumps, if you look at the last 2 lines, they are actually clear text, and that's the clear text representation of the file being downloaded. So once again, this is another example of a proprietary protocol which you can fingerprint using a network device and be able to stop or rate limit. And now coming to the latest example of Skype. Skype does an excellent job in trying to hide detection. As soon as you open your Skype clients, first of all, you will see a lot of packets going on TCP as well as UDP ports. Most of these packets go to high-numbered ports. And the only way we have been able to identify the Skype traffic belonging to a video or a voice communication is to figure out where the maximum data is flowing. And when you are recording packets and as you are talking at the same time, figuring out which particular UDP session is being for transporting the voice traffic. And again, even if you look at a lot of Skype traffic, what you find is the content of the packets is random. Of course, Skype client and server, they understand that. But for an external user, the content is totally random. Even when you initiate the call between the same 2 parties, in a span of few minutes, what you will notice is the port numbers are totally changing, the length of the packet totally changes, as well as the content too. So using the conventional tactics, it's very difficult to identify this particular protocol. And that's why what you need here is a shift where so far we have been relying on detecting these using content embedded in the packets. And what you ideally would like to go to for some of these newer protocols is to go for a framework, if possible, by exploring the statistical properties. The closest analogy I can think of is if you are given hydrogen and a helium jar, the gases, and if you are supposed to identify which of them is hydrogen, which of them is helium, one way of doing that is to study the electron properties of both the gases using their whatever lights they emit under particular, when you shine a laser and the kind of light they emit, you can figure out which is hydrogen and which is helium. And that kind of detection is more like based on the physical properties of the gases themselves. But however, another detection is also possible where you put these jars of gases under different pressure and different temperatures and see how the volume changes. And that's exactly the kind of paradigm you're trying to now bring to protocols, where you're observing the gross properties of these protocols compared to the minor or minute properties. And this is a quote which I like from one of my earliest statistics classes, where it says statistics is like a bikini that reveals what is interesting but hides what is vital. And after the class, this is the only thing I remember. So what we are trying to see here is if both interesting and vital things can be revealed via this analysis.
Are you driving for the slides?
Yeah.
So I don't want to alarm anyone, but I'm wearing a wire. So I also get to have the fun job of explaining the drunk guy, which I think is supposed to be a cartoonish representation of me. But it is an important statement in that this is statistics here. Statistics are like guesses. They're not definite. PISA is never going to say, this is definitely DNS, this is definitely Skype, this is definitely eDonkey. But it is going to say, I can tell you with quite a bit of probability that this is DNS or Skype or eDonkey or one of those protocols. And the way we do that is we actually measure these protocols on various axes. In fact, 10 different axes, 10 dimensions. And we get to use nice phrases like plotting a point in a 10-dimensional hypercube and things like that, which makes me sound really smart around the office and then just gets blank stares from everybody else. Any blank stares? Everybody's blank staring. Okay, that's good. Off to a great start. So let's look at the first coordinate that we track, and that's the average packet size to client. So not only are we looking at the packet size, we're looking at the directionality of the packet. And in this case, client and server are sort of arbitrarily defined. You can identify the client or the server during training via IP address or port or what have you. And this is always important because, if you have large packets going in one direction and small packets going in another direction, then you're definitely doing some sort of client-server interaction. The client is requesting something of the server is sending something back, things like that. Whereas on things like streaming protocols, you're going to get massive amounts of packets, but they're going to be very, very small. And if you're doing file transfers, they're going to tend to be very, very large. And that's a very good way of distinguishing between two different types of protocols. And all of these points, all these axes were chosen because in many ways you can't avoid doing it this way. You have to do it this way. So even if you try to obfuscate what you're doing, you're still going to see these properties. And so if we can go. And so what we have here is a graph that we've shown, which is the average packet size to client over time. And we've got the blue points, which is just other traffic, and we've got the red points, which is Skype. And as you can see, the Skype stuff clusters very, very well. You don't see any packets over 400 bytes in size, and you see most packets within the 200 and smaller range. And of course, that's necessary for things like VoIP because you have to have very small packets. Very big packets take a long time, and if you drop a really big packet in a voice traffic, you get an uncomfortable pause. So. Oh, that was clever. I came up with that on the fly. So. And then the next one is the average packet size to server. And everything I said just then for the client makes sense for this as well, except that we're looking at it in the other direction. And something that's really interesting is we're working on ways to identify which one we think is actually the client or the server by looking at the average packet size, going in both directions. And so obviously, certain things, if you see something that receives like 1 or 2 bytes on a PC, on your office network, it receives just a very small packet and then suddenly sends a huge amount of traffic, probably not a good idea. It's probably saying, give me all the passwords that you know about Mr. Keylogger. And Mr. Keylogger wakes up, sends all the passwords, and then goes back to sleep. Definitely a bad thing. We want to make sure that we can track that sort of thing. So we picked that axis as well. And then now we're looking at the packet size to server. This is the same graph. And once again, we've got Skype in red, and we've got everything else in blue. And once again, Skype, very interestingly, has almost the exact same distribution in the alternate direction. And that's because it's a two-way voice communication protocol. It can't help but have the same packet size in both directions because it's, two people talking. Unless you're talking to, like, my girlfriend, in which case it's one person talking, but anyway, she's not here, so I can say that. So as you can see, once again, we don't have any packets over 400 bytes, and we have